Hi, Itzy. It's Miss Ryan. This is quite a question. It is what I always say in class, a pretty ugly question. I hope you would not see anything like this on the exam. But I did go through it and I found a way to get to the answer without having that trig identity memorized. And when I say trig identity, I'm talking about this one. That's not something that I ever taught you because there's all these different identities and it's a lot to memorize, and I don't think it really shows up. So I didn't think it was worth it. So I found a way to do this question, assuming that you don't have that memorized because I don't, and you probably don't either. So let's see on this question. The first thing it said a rocket is rising vertically at a rate of 5,400 miles per hour. And we'll get to what that label is. An observer on the ground is standing 20 miles from the rocket's launch point. How fast in radians per second, and that is a big deal because they give you per hour and they want per second, is the angle of elevation between the ground and the observer's line of sight of the rocket increasing when the rocket is at an elevation of 40 miles. So the picture, and I love your labels that you wrote in, the rocket's going up and you see the height here, and then the observer is standing 20 miles away, and that's the angle that they're talking about, the angle of elevation. So in terms of rising vertically 5,400 miles per hour, that's actually the rate of change of the height. So it's not saying that is the height, it's saying that is how the height is changing, right? Rising vertically would be talking about the height, and it's changing at this rate, and it gives you miles per hour as the unit. So that label would be not the height of the rocket, but how the height is changing. So dH/dt, and it's changing with respect to time. You also know because the unit says per hour. The observer on the ground is 20 miles from the launch point, so you can just see that in the formula, I think. How fast in radians per second is the angle of elevation increasing? So it's not asking you for the angle, it's asking you how fast is that angle changing. And so that means that they're asking you for d theta dt. You know that because it's radians per second. So that's a unit of a rate of change. And that word increasing is also an indication that they don't want you to find the angle. They want to know how the angle is changing or increasing. So d theta dt. And then the rocket is at an elevation of 40 miles. I would call that the height. So if the rocket is 40 miles above the ground, that's just the height as opposed to how is the height changing. So you can see that they wrote the equation tangent of theta is opposite over adjacent. And then they took the derivative because so much of this question deals with dH dt, d theta dt. You can see the derivative is going to be needed. So if you take the derivative with respect to time, this is going to be implicit differentiation because time and theta are not the same variable. They don't match. So you're going to use the chain rule here, and you're going to take the derivative of tangent, and that is SST. So the derivative of tangent is secant squared. And then you bring down the theta, but then you take the derivative of theta, which is d theta dt. The reason it's not 1 is because these variables do not match. So the easy way we remembered it is if they don't match, then you need d theta dt. This is indicating that the independent variable is time. On the other side, when you take the derivative, 1 over 20 is a constant, but then again, the derivative of h is not going to be 1 because the independent variable is t, or more simply said, those variables don't match. So instead of saying the derivative of h is 1, I'm going to say dh dt. That's the same as h prime. It's just a fancier notation. So this is my equation. And remember that dH dt, that was given, right? That's up here, and we know that that is 5,400 miles per hour. 1 over 20 is a constant. D theta dt is what they're asking us to find, and then we kind of have to figure out what to do with this. So the first thing, well, I'll tell you what I did. I plugged in 5400 for my DHDT, and I had a little bit of an error there because they wanted radians per second, which is a cruel thing to do to you on this question. So let me zoom out a little bit. And DHDT, how is the height changing, was 5,400 miles per hour. And because they want the time, they're asking us radians per second. So we're going to convert that to seconds. So 1 hour is 60 minutes, and 1 minute is 60 seconds. So that the hour cancels, the minute cancels, and then grabbing my calculator, 5,400. So when you do 5,400 and then 60 times 60 on the bottom, you get 1.5, and that would be miles per second. So that is what I'm going to use for that DHDT to be in the right unit. So let me see if I can grab this and move it down, see if that worked. And then, okay, I think that's good. So then we just basically figured out that we have secant squared of theta, d theta dt, 1 over 20, and then dh dt is this, 1.5 miles per second. And then this is what we are trying to solve for. How is the angle changing with respect to time? So the only other thing we need is this secant squared theta. So this is where they use the trig identity, and I did something different. So I went back to this triangle right here. I'm going to write it down here because this, sorry. I'll erase this so we can see the question, or maybe I can just copy the question. Okay, so I went back to this diagram, and remember how it said that the rocket is at an elevation of 40? So they want to know d theta dt when the rocket is at a height of 40. So I filled in a 40 right here as my height, and I knew that 20. And then what I did is I solved for the angle. So I wrote that trig function, tangent of theta is opposite over adjacent. And 40 over 20 is 2. And then this is the only thing you have to remember. If you're trying to figure out what that angle is, then you do the inverse tangent of 2. You want to be in radian mode on your calculator, and you can type in inverse tangent of 2, and it tells you that the angle is 1.107148. I'm writing down all these digits because it's not the end of the problem yet. 1.107148,718. So that's the angle theta at that instant. And so basically I was able to take this, I'm going to copy this and move it down. And now that I know the actual angle, then I could just plug it in. So secant squared of, theta we just figured out. So theta is 1.107148,718. D theta dt, and then let's do 1.5 divided by 20. That's 0.075. Okay, and then if you are solving for d theta dt, you would just divide by secant squared of that angle on both sides. Sorry, I ran out of space, but I'll write it better here. So your answer, and you don't have to simplify it, is 0.075 divided by secant squared 1.107148,718. Okay, that looks really rough, but it would be 100% acceptable to leave your answer like that. This is a little bit tricky to simplify on your calculator because the secant is the same as the reciprocal of cosine. So that is a lot to have to think about. This is how you would type it in. This is how I checked that my answer was right. Um, I'm going to check it right now just to make sure I did not go wrong anywhere. 0.075, and then another fraction, 1 over, parentheses, cosine, 1.107148718, all of that being squared. And it does give you the answer that is in your book, which is 3 over 200. Oh my gosh. Oh, 3 over 200. Okay. Yes, it does match. So I would strongly recommend just stopping here and not worrying about simplifying because it's the free response section. Again, I would say I would be 100% shocked if anything like this showed up, but those are my notes, and that would be a solution to get to that answer without having that trig identity memorized. That is quite a question. Let me know what questions you have on that.